In this video, we'll use a simple proportion to calculate the pressure inside a container, an ideal gas, and thus we'll be using the ideal gas law. But we have a rigid, that means the volume doesn't change. Sealed, that means the number of particles inside the container does not change. It has an ideal gas with an absolute pressure 1.5 atmospheres. This is not the gauge pressure, where you'd have to add in the atmospheric pressure. This is the true pressure of the ideal gas in this container. And this occurs at a temperature of 30 degrees Celsius. We want to know what the absolute pressure for the gas is when the temperature is lowered to 0 degrees Celsius. Well, we first ought to think about the concept. What do you think will happen to the pressure when the temperature decreases? And you should, with some thinking about the motion of molecules and their effect on pressure, they're going to slow down when the temperature goes down, so we should expect a lower pressure. So let's see what we can generate. First, I would ask you to make a drawing as you work problems. So here's our rigid sealed container with ideal gas. I label what I know: the original pressure 1.5 atmospheres, original temperature 30 degrees Celsius. Here's our ideal gas law, and this is in the form of moles and the gas constant and temperature. We could also use PV equals the number of particles, Boltzmann's constant, and temperature. It doesn't matter which of these two you use. I'm going to use PV equals nRT. I'm going to divide two equations here, so I'll slide this up just a little bit. But I can write down the ideal gas law for the initial condition and also the final condition. P1V1 equals N1RT1. And then separately I could write the equation P2V2 equals N2RT2. I can divide two equations. This is always legal as long as I don't have a zero that I'm dividing. But if I have A equals B and I have C equals D, if they have those two statements, I could divide these, and A over C is equal to B over D. So you could put numbers in there. You can verify that if you wish. But I'm doing that here for a little bit more complicated, the more symbols, but only temporarily. Because it's a rigid container, volume 1 is the same as volume 2, so those are going to cancel. You see they've disappeared. It's a sealed container, so the number of moles of gas is the same for condition 1 and condition 2. The gas constant is a constant, so those cancel. So I end up with this ratio of pressures is the same as the ratio of temperature. What you must be careful about here is this temperature must be in Kelvin. It cannot be Fahrenheit, cannot be Celsius. So the temperature T in both T1 and T2 must be in Kelvin. So that's my next task. What are those temperatures? Well, T1 is 30. I add 273 to find the Kelvin temperature, so it's 303 Kelvin. T2 is 0. That was what we're going to lower the temperature to, 0 degrees Celsius. So that gives us 273 Kelvin. I can put in the values, and at the same time I'm solving for P2. So if I multiply both sides by P2, then if I would divide both sides by T1 and multiply both sides by T2, back up and replay that if you need to, but I'm solving for the simple P2. It is P1 multiplied by T2 and dividing by T1. Remember, we're supposed to get a smaller pressure. Let's see if that happens. So, original pressure, the new temperature divided by the original temperature, the T1, and I come up with 1.35 atmospheres. You ought to do your own calculation on this and pause the video, check your math that works out. We are at a lower pressure than what we had originally. That makes sense because the temperature is indeed smaller. So just a quick example there of using ratios to do the ideal gas law. If you'd like to see some more of my short lectures and worked out example problems, physics.gpclements.com. astronomy.gpclements.com for each subject area. These are geared for high school and introductory college level physics. Free, no registration. If you like the videos, please subscribe to my YouTube channel. Again, there's no cost for subscribing to a YouTube channel.